Hello guys, so today we are gonna be talking about the rearrangement inequality. We're gonna do a proof of it, we're gonna do quite a bit of problems, and well, I guess it's gonna be fun, so bear with me. Okay guys, so what does the rearrangement inequality state? Well, it states that if we have two sequences, maybe AI and BI I will call them, because well, I already wrote it down in such a way that they are called AI and BI, so it will be kind of stupid to call them other names. So we have AI and BI, and those sequences are non-decreasing. What it means? Well, it means that for every single term in the sequence, this term is greater or equal to the previous term, yes? So A2 is greater or equal to A1, A3 is greater or equal to A2, AN is greater than or equal to all of the previous terms in the sequence AIs. The same thing happens here in the BIs, lovely. And now I would like to define myself a third sequence, and I will call that sequence XIs. And I will set XIs to be some kind of a permutation of those BIs. And what does it mean for a sequence to be a permutation of some other sequence? Well, it means that the terms of the sequence are the same. I mean, they have the same values, but they are in a different order. So for example, if I had a sequence 1, 2, and 3, then a permutation of 1, 2, and 3 of 1, 2, and 3 will be 2, 3, 1, 3, 2, and 1, or maybe 2, 1, and 3, or 2, 3, and 1, and, stuff like this. So those are permutations of some kind of a sequence, yeah? And so XIs are some permutation. And you see, well, now XIs don't necessarily need to be a non-decreasing sequence. Well, it is not even ordered. So, yeah. I mean, it doesn't really have to be ordered. It can be. There is a possibility for it to be even increasing. If I just made XIs be some kind of a like flipped version of all those BIs. But now, if we take those XIs, yeah, then for a nice sum, A1 multiplied by B1 plus A2 multiplied by B2, and we are adding stuff up to AN multiplied by BN is going to be greater than or equal to A1 multiplied by X1 plus A2 multiplied by X2, and we are adding stuff up to AN multiplied by XN. Yeah? And this will be greater than or equal to one more thing, so A1 multiplied by BN, so the first term of this sequence AIs multiplied by the last element of the sequence BIs, plus A2 times Bn minus 1, so the second element of the sequence AIs multiplied by the almost last element of the BIs, and we're adding stuff until we get to the last element of AIs multiplied by the first element of BI, so AN times B1. Yeah? Whew. Oh man. Finally said it right and didn't make a mistake. Whew. So, how are we supposed to prove this beautiful theorem? Well, it honestly kind of looks like magic, a miracle or something, but there is a proof, and it's a lovely proof, and I would like to show it to you guys. So maybe let me first of all try and separate this from the rest of the board so we don't get mixed up in the process. And now I would like to do the most important thing, so write proof. Lovely. Yeah, now, so if I wanted to prove this theorem, first of all, we need some kind of a sequence, so I will define myself a sequence AI, and I will define it such that it's gonna be a non-decreasing sequence. Yeah? Lovely, just as here. And I will take myself another sequence, and I will call it BI. BI, not B1. Yeah. However, this time I'm not gonna be setting this sequence to be a non-decreasing sequence. I will not really care what it's ordering. I will just say that, well, it's not ordered. Those are commas. Yeah? I don't set any particular kind of relation between those terms. Yeah? Beautifully. And now I would like to define myself a sum. And I will call this sum S. And I would like to set S equal to, well, the same kind of sum as we have right here. So A1 multiplied by B1, then we have A2 multiplied by B2, and then we are gonna be adding stuff up to AN multiplied by BN. There's a beautiful rain outside my window. I love its sound. I hope you can hear it. Yeah? And now I would like to take myself two numbers from the sequence bi's, and I will call them bx and by. You will see why in just a moment. And now I would like, well, first of all, let me state that x is going to be greater than y. Yeah, because, well, if they were equal, then I would, well, those b's would kind of be the same number, so it's not really, it'll be stupid, yeah, it'll be just stupid, yeah. And y is at least 1, because, well, we're starting bi's from b1, n is at most n, is at most n, x is at most n, yeah, lovely. All the brain power I used to speak properly, I used on, well, reading this stuff out loud, so don't mind me, guys, yeah? And now, let me rewrite this sequence, I mean this sum one more time, just so you can visualize those things being somewhere. Yes, so we have the first A times the first B, and then we will be just adding stuff up until we get to AY times BY. AY times BY. You see Y, I mean AY and BY, they come first, they come before BX and AX in those sequences. That's because, well, Y is less than X, and we are starting from 1, and we are making our way up the ladder, yeah? Lovely. And then we will be adding some kind of stuff further and further until we get to AX times BX, and then we will add a little bit more of that stuff and end up with AN times BN. Lovely. And what I would like to do right now is take that BY and BX and switch them places. So I would like to create another sum, maybe I will call it S prime or something. And S prime is gonna look something like this. I will just say it to be, well, the same kind of sum as S without the prime in the subscript. However, I would like to just take this BY and BX and switch them places. And I will get, for that process, the sum A1 times B1, and we're adding stuff up to AY times BX. Then I'm adding just a little bit more of stuff. I'm getting AX times BY, and then I will have AN times BN. Lovely. And you see now, guys, if I were to subtract S prime from S, well, then all of those things like A1, B1, A2, B2, and things like this, they would cancel out. That's because, well, they did not really change after just flipping BX and BY. Yeah? And so this difference right here would be just, well, AY, BY, AY, BY, yeah, plus AX, BX, minus AY, BX, minus AX, BY. And you see, absolutely an awesome thing is that I can now go about it in this kind of way, that I can write it as, well, actually product of two nice parenthesized expressions. No idea how you say it in English, honestly. Well, and that's gonna look something like this. It's gonna be AX minus AY multiplied by BX minus BY. Yeah? And see, that's actually pretty nice, because AX times minus AY, well, this is greater than 0, or greater or equal to than 0, because AIs are an ordered and non-decreasing sequence. Yeah? And we see that X is greater than Y, and so this is greater or equal to this. So this is greater or equal to 0. Okay, but well, it means that if bx is greater than by, well then the sum s minus s prime is positive. Yeah? And this actually means, as well, this then actually means that s is greater than s prime. Yeah? So we see that s being greater than or equal to s prime actually will imply bx being greater than or equal to by, but we see that x is greater than y. And, well, what does it mean? If we were to apply the same reasoning over and over and over again, we would end up with an ordered sequence. We would order those b's, yeah, such that for all x's that are greater than y's, bx is greater than or equal to y. So we basically just flip around those terms and rename them until bi is a non-decreasing sequence. And if it is a non-decreasing sequence, then this sum right here, s, is greater than the sum with some kind of a permutation of those bi's multiplied by those ai's. Yeah? And it actually also proves this inequality right here, so the inequality between this sum and this sum, where we basically just flip around all of the bi's. Yeah, because, well, here it is strictly decreasing sequence. Yeah, so it's exactly the opposite of what was. So, well, this has to be the smallest of all of the three things. Yeah, I honestly love that proof. So, whew, can you see what I'm writing here properly? Yeah, you can see it. Lovely. So that will be all for the proof. And now we are heading for the problems. And I once again have no idea why I am on earth Italianing so much right here. Anyway, let's go to the problems. Okay guys, lovely, so we can move on to the next problem. And so we are given two sequences, xi's and yi's, that are non-decreasing sequences. Well, this is a nice cue that we will be able to use the rearrangement inequality probably in this problem. And we're given a third sequence that is denoted as zi, and that is a permutation of yi. What a coincidence that I put this problem in a video about rearrangement inequality. And we're supposed to prove that this awful expression, I mean this awful thesis is true. Well, let me read out, I guess. So x1 minus y1 squared plus x2 minus y2 squared, and we're adding stuff up to xn minus yn squared is less than or equal to x1 minus z1 squared plus x2 minus z2 squared, and we're adding stuff up to xn minus zn squared. Lovely. So first of all, well, I would really like to get some kind of a visual on this problem. I mean, see it, you know, like written out a little bit better. So maybe I will, you know, have some kind of a idea then. So let me expand those parentheses. But you know, I'm not gonna be expanding those two because I will probably run out of space. And you will anyway see, you will see what I mean anyway. So here we're gonna get x1 squared minus 2 times x1 y1, and then we will add that remaining y1 squared. I will not be explaining this one. I will just put those 3 dots here and then focus on xn minus yn squared. So I will get xn squared minus double xn yn plus yn squared, and it's supposed to be less than or equal to what? Well, it's going to be less than or equal to x1 squared minus double x1 z1 plus z1 squared, and then after a couple of dots we're going to get xn squared minus 2 times xn zn plus zn squared. You see, a lovely thing right now is that we have this x1 here. Probably I mean, for sure, we would have had this x2 right there, maybe then x3 squared and stuff like this, and we have this xn squared right there. So maybe let me just take all of those x's that are squared and group them into a single sigma notation thing. So I will write it in sigma notation as the sum from, oh, this is an awful sigma. Yeah, from I equal to 1 up to n of what? Of xi's that are squared. Lovely. Well, actually, I can rewrite this entire thing in terms of sigma notation. It's gonna be, I guess, a little bit more clearer. Here I will get negative 2 times x1 times y1. Well, here I would have gotten negative 2 times x2 times y2, and here I have this negative 2 times x and times y, and so I will just rewrite it as negative 2 times the sum, sigma notation, from 1 up to n of xi times yi. Well, this is starting to look like some kind of thing with the rearrangement inequality, doesn't it? Yeah, and then let me just group all of those y's together, and I will get this sum from I equal to 1 up to n of yi's that are squared. And it's supposed to be less than or equal to, well, here we have those x's that are squared, well, just as on the left hand side, so I will just write it in the same way as the sum from 1 up to n of those xi's that are squared. Then we will have negative 2 sigma signs with the subscript of 1 up and the upscript of n, so the sums from 1 up to n of what? Of xi's multiplied by zi's, and then I will just have to put my marker and then ruthlessly, I guess, add the remaining sum from 1 up to n of the square of all of the zi's. Lovely. Now, actually, quite a lot of stuff will cancel off from both sides of this inequality. You see, here we have the sum of those x's, I mean sums of squares of those x's, but no, this is literally the same thing. What did I just say? Doesn't matter, those are the same things, we can just go on and kill them off. Here we have the sum of squares of those yi's. Okay, but here we have the sum of the squares of zi's. Well, those are the same things, because zi is just a permutation of yi, so, well, we have exactly the same terms there. I mean, they are in a different order, but when we're summing stuff up, we don't really care about the order. And so, well, those will have the same sum. And after cancelling this stuff from this side of the equation, inequality, and this stuff, and then this stuff, and then this stuff, what we're going to be left with is negative 2 times the sigma sign subscript of I equal to 1, upscript of n, xi multiplied by yi is less than or equal to negative 2 times the sigma sign subscript 1, upscript n, x1, xizi, not 1 but I. Whew, okay. Lovely. So now it would be actually kind of nice to get rid of those negative signs, because, well, they're kind of messing everything up. But if we do this, we also have to flip this inequality sign right there, and we can just get rid of those 2's, we don't really need them. But now, wait a minute. Whew. Well, this is literally the statement. Well, I sound like a squirrel there. Nobody cares. So we have literally the, like, statement of the rearrangement inequality, yeah? Because here we have two sequences that are non-decreasing, and here we have, well, the same sequence x as here. However, we're multiplying it by a permutation of this non-decreasing sequence right there. And so I will say that by the rearrangement inequality, this is true, and I would have wrote, and I would have written by rearrangement inequality is true. But first of all, I'm too lazy, and second of all, I don't know how to spell rearrangement, and so we will just move on to the next problem. Oh, and by the way, this was the IMO 1975, I guess. Yeah, it was 1975. Yeah, it was lovely. Yeah. Let's move forward. Okay, my beautiful people, so now we're gonna move to problems and we're gonna start with this beautiful one. So A, B, and C are positive real numbers and we're supposed to prove that the sum of the squares is greater than or equal to A times B plus B times C plus C times A. Lovely. No matter how many times I try and record this bit, every single time I started reading B times C, I don't care. So how are we supposed to approach this? Well, and where is the rearrangement inequality that we would like to that we would like to use here? How are we supposed to fit it in? Well, recall what squares were. This A squared we can rewrite as A times A. Here B squared we can rewrite as B times B, and C squared as C times C. That will be greater than or equal to A times B plus B times C plus C times A. Well, that's right, because now we are kind of we have like two sequences, yeah. In each and every one of those, we are multiplying some two things, yeah. And it seems like they are in slightly different orders in those sequences. So maybe something with rearrangement inequality would be nice here. Actually, it would be really nice, because well, if I were to create myself two sequences, and I will call the first one xi, and the second one yi, and for the xi's, I will say that the first x is going to be equal to a, the second x is going to be equal to, maybe the first x is going to be equal to c, the second x is going to be equal to b, and the third x is going to be equal to a, yeah? And for the y's, I'm going to do exactly the same thing. So yi's, y1 is equal to C, y2 is equal to B, and y3 is equal to A. Well, now I would like to assume, without loss of generality, that A is going to be greater than or equal to B, is going to be greater than or equal to C. I can do it without loss of oh man, this poor line. Okay, so I can do it without loss of generality because, well, whenever, for example, it happens that B is greater than A, well, I can just switch them places. I can just say that B is now A and A is now B, so well, it doesn't really matter because, well, real numbers are an ordered set, yeah? There always has to be some greatest number, yeah? Or they are, all equal. Yeah, something like this. And so what it's gonna tell me is that xi, I can order such that for xi's, we have x3 greater than or equal to x2 greater than or equal to x1. And we have, for yi's, we have y3 greater than or equal to y2 greater than or equal to y1. And so this means that yi's and xi's are non-decreasing sequences of positive real numbers. Lovely. And now, let me, take all of this substitution right here and just rewrite our problem in terms of all of this stuff. So let's say maybe that we're gonna have this as a sum of the form xi times yi, not the other way around, not yi times xi. Yeah, so here we're gonna get what? x3, yeah, x3 times y3. Then we're gonna get x2 times y2. And then we're going to get x1 times y1. On the other hand, on the right-hand side, we're going to get what? A, so, well, x3 times what? y2. Okay, nice. Then we're going to get what? x2 times what? y1. And then we're going to get x1 times y3. And you see, well, actually, this is some kind of a permutation of those yi's. And you see, this is exactly what the rearrangement inequality states. This thing right here is exactly what the rearrangement inequality states for the case of n equal to 3. For the case where both the sequences we're dealing with have exactly 3 numbers. And so I call this a problem solved. And we can move on to something a little bit more difficult maybe. Okay, my guys, so moving forward, we have this beautiful problem right there. So A, B, and C are positive real numbers. And they are also lengths of sides of some triangle, which is, well, even marked as something very important right there. And we're supposed to prove that a squared times b plus c minus a plus b squared times a plus c minus b plus c squared times a plus b minus c is less than or equal to 3 times a times b times c, and we would like to use the rearrangement inequality right there. Okay, well, first of all, we have that they are sides of some kind of a triangle. They are lengths of sides of some kind of a triangle, those A, B, and C. So maybe we could try and get some kind of control over there. So maybe, let me assume, without loss of generality, that A is going to be greater than or equal to B, which is going to be greater than or equal to C. Lovely. Yeah, we can do it. We can do it. And now, I would like to know one thing. How are gonna those things right here behave, I mean, towards each other? Are they gonna be mean to each other? For A greater than B, for example, or B greater than C, yeah? So what I mean is, if I have A squared times B plus C minus A, and I have B squared times A plus C minus B, and I know that A is greater or equal to B, then, well, is this stuff going to be greater or equal to, or less than or equal to the stuff on the right hand side? Well, I have no idea. So maybe let's just pick something. So maybe this, why not? And try and work it out. Well, the problem is that, oh my god, we're gonna have a squared b plus that a squared c minus this a cubed. This a cubed is kind of awful, isn't it? Yeah, those cubes are kind of basically giving up, if I'm to be honest. Now what we can actually do here is get rid of those squares, because, well, they won't really matter. I mean, we know that a is greater than b, so it's gonna be even more, you know, it's gonna be multiplied by even more stuff on the left hand side, so it's not gonna affect anything. Both sides are kind of like, I mean, evenly brought down this way. So we get a times b plus c minus a times is less than or equal to b times a plus c minus b. And what we're gonna get out of this is actually a times b plus a times c minus a less than or equal to, well, a times b once again plus b times c minus b squared. We can delete those for both sides of this inequality. That's another nice thing. And then we can just, you know, move this negative a here, this positive ac here, this negative b squared here, this bc here. What we're gonna get is b squared minus bc is less than or equal to a squared minus ac, and so b times b minus c is less than or equal to a times a minus c, which is, well, true, because a is greater than or equal to b. Lovely. So we know that this inequality will hold. You know, it is actually really, really nice. And why do you think it's nice? Because by rearrangement inequality, and it's actually an awful thing that you have to notice this in this problem, but this is an IMO problem, so you actually have to notice everything here, that a squared plus b squared plus c squared is going to be greater than or equal to what? To ab plus bc plus plus ca. It's going to be also greater than or equal to ac plus ba plus cb. Yeah? And so we can actually go on and construct two nice, like, inequalities that are going to be awfully long, honestly. So a squared times b plus c minus a plus b squared times a plus c minus b plus c squared times a plus b minus c is going to be actually less than or equal to a times b, because, well, this is less than a squared, yeah? So a times b times b plus c minus a, plus, let me put my marker, just a second, yeah, lovely, a times b plus c minus an a, plus b, c, and a plus c minus a b, right there, not an a, and then plus ca times a plus b minus a c, yeah? You see, well, that's because of this thing right here. If we're multiplying this like parenthesis, yeah, this not like but literally a parenthesis, by something that is less than the thing we are multiplying the second parenthesis by, well then this expression is greater than this expression. And so this expression is greater than this expression, this is greater than this, and this is greater than this. So this entire thing right there, the right hand side is greater than the left hand side, beautifully. And now we can actually go a little bit further and use this thing, I mean this inequality right there, getting a squared b plus c minus a plus b squared a plus c minus b plus c squared a plus b minus c is getting really awful writing this entire thing down, is less than or equal to ac b plus c minus a plus ba a plus c minus b plus c times b a plus b minus c. But now a nice thing kind of, you know, appears here, because if we were to add both of those inequalities, what we'd actually get, and let me just for the sake of simplification call this stuff right here s, maybe, we'll get that 2 times s is less than or equal to what? Or maybe, well, actually every square centimeter of space will be a God blessing right now, so I will have to do it economically, honestly. So we're gonna get what? AB times b is gonna be AB squared plus ABC negative A squared B. Lovely. Then ABC C squared B negative B squared C plus A squared C plus ABC negative C squared A. Lovely. And now this stuff right there, we're gonna get plus, and we're gonna get ABC one more time, ABC, and then plus AC squared. Those are gonna cancel out, yeah? Then we're gonna get A squared negative A squared C negative. Okay guys, I got a little bit caught right there because, well, my camera decided to die. Anyway, we are getting back to the problem. So we add A squared B plus ABC one more time, ABC negative, this time, negative B squared A, and well, B squared A, this A squared B, we're cancelling a lot of stuff, plus ABC one more time, AB and C, and then CB squared, those two are cancelling each other out, and then C squared B, negative C squared B, C squared B, and C squared B is C squared B, where is C squared B? Here it is, just in front of my face. It is equal to 6 times ABC. If you sum those up, yeah, there are 6 of them, there are 6 of them. And so what we get, dividing both sides of this inequality by 2, that S, so well, this thing right here is less than or equal to 3 times A times B times C, which we were supposed to prove, and thus I call it Hey, problem solved.
Okay guys, so that would be all for today. I hope you liked it. I hope you got some value from this video. If you did, I'm happy, you're happy, awesome, and hopefully see you in the next one.